Hey everybody. Okay, so today we are going to be looking at various chemical reactions that we might hopefully one day see in the lab. So, we're going to watch 7 videos and I am going to provide commentary as we watch. So, hopefully this works out. So, please forgive if there's any technical issues. I've already tried editing this into other forms and it didn't quite work out. So, this is the next option. All right, so the first thing we're going to be looking at is the reaction of metals with oxygen in the air.
Let's have a look at some sodium. We're going to look at the reaction of sodium with oxygen in the air. If we see our piece of sodium, we see it looks pretty much like a rock. This is because what we're seeing is a coating of sodium oxide because sodium reacts with oxygen in the air. In fact, it's stored under oil to keep oxygen and water away from the sodium. Let's cut a fresh surface and observe it. Do you see that the fresh surface is quite shiny?
So I believe the fresh surface is this part right here. It's the more silvery part instead of the brownish part. Okay, so if you look on the top, it's kind of brownish, like a tan color. If you look on the sides where she just cut it, it's more of a silvery color.
It goes dull fairly quickly as the oxygen in the air reacts with it. I'm going to cut another fresh surface for you so that you can compare.
So she's using some forceps, which are the tweezers, and a scalpel to slice the sodium.
Do you see how it's already become more dull? In only a small amount of time. It's reacting with oxygen in the air around us. That's producing sodium oxide. Let's look at the reaction between magnesium and oxygen.
Okay, so basically that sodium metal reacts really, really fast with the oxygen in the air. And most of the time, sodium actually has to be kept in oil so that it doesn't react with oxygen in the air as well as moisture that's in the air or water.
This is not as fast as the reaction between sodium
now, we've probably seen this one
and
before.
oxygen because magnesium's not as reactive.
We saw this around
I have
Halloween.
my piece of magnesium ribbon and my Bunsen burner.
So magnesium starts out as a
place
silvery
the magnesium
ribbon.
in the hottest part of the flame and let's see what happens.
So she's looking away because it's a little bright.
Very bright light. You don't want to stare at this light for too long. It can really damage your eyes. Let's have a look at the product of this reaction. We started out with shiny grey magnesium, and now we have a white powdery substance. This is magnesium oxide. Let's look at the reaction between aluminium and oxygen.
Aluminum.
I have a piece of aluminium.
Aluminum.
It's a shiny grey colour. Can you see how shiny it is? Let's put it into the Bunsen burner flame.
So she's putting basically tin foil or aluminum foil in there.
We can see immediately that it is melting in the Bunsen burner flame. Just going to try and heat it as much as I can.
This is like the same aluminum foil that you would be putting on your food.
Do you see the bit that's been in the Bunsen burner flame? Do you see how it's not shiny anymore? Now it has a coating of aluminium oxide.
Aluminum oxide.
It's an ionic compound and therefore isn't shiny. Now it's time to look at the reaction of zinc with oxygen. Zinc is also a shiny grey metal. You can see how shiny that is. Now I'm going to heat that in my Bunsen burner flame and see what we get.
So what she's doing right now is she's adjusting the flame, and how she's doing that is she's opening and closing a valve that's down at the base of the Bunsen burner, and that allows more or less oxygen to come in. So if you see a blue flame coming up, that means there's a lot of oxygen and it's burning really well. If it's a yellow flame, that means it's closed. There's not very much oxygen getting through. It's not a very complete combustion reaction. Okay, so it's a blue flame, lots of oxygen there.
You can see that this is also melting in the Bunsen burner flame. I'm not going to leave it over the Bunsen burner because I don't want bits of molten zinc dropping down the barrel of the Bunsen burner.
Because that makes a big mess.
Can you see any change? Let's have a look at what happens when we put an iron nail into the Bunsen burner flame. Mostly, all that is happening here is that the nail is glowing red hot.
So it's not changing.
Now I'm going to sprinkle iron filings into the Bunsen burner flame. By increasing the surface area of the iron, I should be increasing the rate of reaction.
So this is basically shaved down iron.
Oh, do you see the sparks? The iron will ignite much more readily when it has higher surface area.
So if you recall when I did the flame test lab back in October, I did one of them and it made like a sparkler. That was iron filings. So that's what she just put into the Bunsen burner that created those sparks. And basically what it says is that if you put more surface area, if you shave it down into smaller pieces and you put more of those pieces in there, it reacts a lot faster, and so you'll notice a bigger change immediately.
I have some steel wool. This has really high surface area.
So steel wool, like the stuff you use to scrub dishes with?
Yeah. Let's see how that burns in the Bunsen burner flame.
So we can see that's burning really fast. That's a lot of surface area there.
We're now going to see how steel wool burns in pure oxygen. Well, really it's just air enriched with some extra oxygen.
So we're upping the oxygen
but
content.
It should be enough to really support the combustion.
Okay, so she lit it on fire. Now she's putting it in a lot of oxygen and covering it up so it traps all the gas in there. And we can see it is sparking quite a bit, at least to start. And eventually it uses up the oxygen. So, all right, take a moment. Try writing out the equations for the reactions that you've just seen. So in each equation, or in each reaction, you have a metal, like iron, reacting with oxygen, O2, to make a metal oxide. So think about what type of reaction you get with two reactants becoming one product. Hint, hint. Okay? All right, so that's it for the first video. Now, I'm not going to tell you what type of reaction that was. That's for you to find out. Okay, so part of this lab is determining what the types of reactions are, if I don't already tell you. The other part is making observations, pointing out what you notice, writing out the equations, things like that. Okay, on that, let's look at another example. I think this one got out of order, though. Yep, this one got a little bit out of order. Okay, so let's look at this next one with alkali metals and oxygen. There we go. It's not wanting to pull up as fast. Okay, so this guy is going to be mixing alkali metals from group 1 with water to form different stuff.
Here I'm working with some lithium metal, very difficult to cut. I've got a piece of sodium here, pretty easy to cut. You notice when I cut through that the fresh sodium is very shiny compared to the rest.
So the shiny part is the inside, like right here and right here, that he just freshly cut. The more dullish gray part on the top is the part that was already up there that's been oxidized already. Okay, so if you recall, one of the properties of the alkali metals, group 1, is that they are very soft. They can easily be cut with a knife, which is what he's demonstrating right here.
Zoom in real quick. Let's see if we can really get in there. So this side will reflect a lot of light. The other sides are pretty dull. And you'll see that especially with the potassium here. I'm going to go ahead and give this kind of a half cut.
Okay, so you can see it's really shiny right here. on this part
So
is
for the
really shiny.
potassium, this is the side that's freshly cut, and you can see the dullness to the other sides compared to that
Just
one.
kind of meh.
So I'm going to go ahead and take those three, and I'm going to add them to water, and we can look at the kind of reactivity of those three alkali metals with water.
If you recall, again, another one of the properties of alkali metals is that they are extremely reactive with water. They react very violently. So we're about to see a show here.
So here I'm going to take the lithium, add that to the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off of there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium, so I'm going to put sodium into the next one.
Now, I'm not sure what's making it pink. It could be an indicator dye that he's put in there to show that it's a basic substance.
And sodium is actually probably going to ignite.
Yeah,
You'll
sodium
see
does
some
quite a bit.
orange flame, perhaps, or some sparks, or some shrapnel.
So you can see a lot of smoke coming off of that.
And then the last one, I'm going to go ahead and put my 2 pieces of potassium in.
That thing that he put on top of that beaker is basically to prevent stuff from flying out, but still to allow the gas to escape. I believe we call it like wire gauze because it's got the pattern of gauze like we would put in a wound, but it's made out of iron so that it's heat resistant.
So this is less potassium than the other two in terms of amount. You'll find that the reactivity is a little bit greater.
So the potassium reacts quite a bit. Yeah. Yeah, I'm guessing that pink stuff is probably an indicator dye to tell us that sodium hydroxide is being made.
Now that potassium there was quite reactive there, but the sodium sometimes will allow hydrogen gas to build up. In this case, it's not igniting. But we can try adding another piece here.
He's adding some more sodium.
We can hope that that's going to go ahead and actually send off some shrapnel and some flame.
So he's trying to make things blow up. How reassuring. So you can see that each of those three is very reactive with water. Oops.
All three produce hydrogen gas. All three produce hydroxides. There's your alkali metals. Next, we're going to go ahead and...
Okay, so we're going to stop right there. So basically, we added elemental metals, sodium, lithium, and potassium, into just plain H2O water. And what we got out of it was hydrogen gas. It's an element with a metal hydroxide. Sodium hydroxide if it was a sodium, lithium hydroxide if it was lithium, potassium hydroxide if it was potassium. In all three cases, one element is replacing another. So I'll let you figure out what type of reaction that is. Now, while we're still looking at that type of reaction, and I believe this is the same one that I'm thinking of, let's hope it is, let's have a little bit of holiday spirit here. Okay, so we're going to see how to make a Christmas tree using silver nitrate. Okay, so watch, he puts this tree that he's made out of elemental copper, Cu. He's pouring in some silver nitrate, AgNO3. Hide that ad. Okay, so we've got copper plus silver nitrate is going to make silver and copper nitrate. So just watch what happens. Kind of looks like it's snowing almost. Notice what color the tree turned, though. Is it still the shiny orange? Oh no, what do you see growing on it? The tree's getting furry. So the copper replaces the silver in the silver nitrate solution. That causes elemental silver to precipitate out of the solution and form silver crystals. Really pretty. Perfect for Christmas time. So the copper has oxidized and it's dissolved in solution. The silver has been reduced and it is forming that elemental silver, those pretty crystals that almost look like tinsel on that tree. Really pretty, especially for Christmas. Next up, we have, trying to make sure that I've got these in order here. Okay, we already did this one. Let's look at, well, it already says what this one is. It's a decomposition reaction. Okay, and I don't know what was going on when I was picking all these videos, but it seems like most of them were from Australia. I don't know if the Australians just so happen to have great science videos or what, but yep, you're getting a lot of Australian accents today. So let's look at a decomposition reaction. So this is the decomposition of calcium or of copper carbonate. So decomposition of copper carbonate using heat.
Good morning. We've got experiments to do today. So one of the things you have to do as a chemist is to predict or at least classify what kinds of chemical reactions you have. Today, we are going to look at this thing called decomposition reactions. Is that pointing in the right direction? So we have this material here called copper carbonate. We're going to add some heat, and we're going to break it down into some parts. What do you think it's going to break down into, guys? You can't break it down into itself. What is it going to break down into? Carbon dioxide, volcanoes. All right, we've got a variety of answers. Let's see what they have. Now, some people said carbon dioxide, and I think that maybe they're right. How can we tell if we're creating carbon dioxide? It's colorless. All right, that's difficult to tell. We can see bubbles, maybe.
Okay, so
here
let me explain the setup that he's got here, because these are some instruments that we've probably not seen before. Okay, so here we have two ring stands, and what they've done is they have clamped on a test tube holder. Okay, so these are specific test tube holders for these ring stands, and we use this whenever we don't want to have to be holding the test tube for a long period of time over an open flame, or if we've got some sort of contraption like this set up so that it's, it stays in one place. So he's got that. He's got a Bunsen burner down here. I see a lot of oxygen not going through because it's a big yellow flame. So not very much oxygen going through there. So let's see what he says.
All right, that's difficult to tell. We can see bubbles, maybe. So here we've got a sealed container. So glass tube, there's a rubber bung, a tube.
We usually call that a stopper. That black piece is called a stopper in the U.S.
And that goes into some water here. So I can see if there's bubbles being produced, and that might tell me it might be carbon dioxide. But that could be any gas. I could get oxygen gas. I could get carbon dioxide gas. We don't know which one it is. So
it's important that the copper carbonate test tube is sealed so that we can trap the gas and transport the gas through that, basically like a straw, into the other test tube, pumping it into some liquid, and if bubbles come out, that means that there's some sort of gas.
To help tell the difference, I filled this one here not with water, but with quicklime.
Lime water.
Or lime water, whatever.
Or calcium hydroxide.
Lime water reacts with carbon dioxide, and it makes it precipitate. So if we see this change into a cloudy color, we know it must be carbon dioxide. If not, it might just be the oxygen or something like that. So let's put it down here in the tripod and see what happens. No.
Okay, we see a few bubbles coming.
Can you see anything changes? No, I think.
Notice the original color of the copper carbonate. It's like a greenish color, sort of like the Statue of Liberty, maybe. The lime water is just, clear.
I think what's happening is that maybe just the air inside is also expanding, so it's pushing out. So when it starts reacting, you'll know.
You'll know. Okay, so we're still making it react, and watch what's happening slowly right down here. The copper carbonate is starting to change color from that green.
Look at that.
So it's turning black.
Look at the other two.
And notice there's a lot of bubbles forming all of a sudden. Notice also it's turning kind of a milky, chalky white color.
What's it made out of?
That's a precipitate.
Carbon dioxide.
All right, so they create carbon dioxide gas. Yeah, before everything goes wrong, I have to unplug it. All right. Well, what tends to happen if I don't unplug it is that I've created all this extra hot gas, so it's an expanded state. Then once I remove the Bunsen, everything cools back to room temperature. And what do gases do when they cool down? They shrink. Well, they come together. So it actually starts to suck up the liquid through the pipe and then down into here, which is not what I wanted, because I need to dispose of this. What this is, has it disappeared entirely or changed somehow?
Oh, it's changed.
It's changed color.
It's gone from green to black. We've created something different. What we've created here is copper oxide. So that's one of our materials. CuO, which we presume is this black color there. Solid. And the other material that we created is CO2 gas, which is what we detected over here. The lime has reacted. Okay, so while the students are setting up their own experiments, let's talk about decomposition reactions. It's basically decomposing something. So we started with something relatively complicated. We break it into smaller parts. So to try and predict what you might create out of it, just think about what parts you have. Do you recognize any of the pieces? So maybe I could get some copper metal at the end. Well, yeah, maybe. Maybe we can get some carbon something. Well, I can make carbon dioxide from this. Or I can get some oxygen gas out of this, which is why we're trying to tell the difference using the quicklime. The lime water over here. So this one here would tell us the difference between oxygen gas or carbon dioxide gas. And we've got a pop.
So the oxygen gas would just bubble out and it'd still be clear. Carbon dioxide gas reacts with the calcium hydroxide and forms this precipitate that looks like kind of a milky solution.
Positive reading for carbon dioxide. So from that, we know that one of our products has to be CO2. The rest is probably good in whatever you got left over. So if I've used my carbon, I've used some oxygens, what's left over? I've still got the copper. It's got to be somewhere. It hasn't turned, from what I can observe, it hasn't turned into like a coppery color like metal, so it hasn't completely, decomposed down its component elements.
So what he's saying is it's not the pretty orangey copper that we always recognize, so we know it's not just plain elemental copper.
So it must be some sort of compound, and usually when you have metals, they're going to be some sort of oxide. So hence, copper oxide.
Okay. So that was decomposition. Boy, this sure seems like we got a lot of videos here. Okay, couple more to go. Let's go with another precipitate reaction, silver nitrate. So this one actually gets fairly cool. I like this one.
We'll look at the chemical reaction for silver nitrate.
I'm also glad that somebody else is doing this instead of me because it kind of makes a mess in the lab if you're not wearing gloves. So, yep, I'm glad somebody else is doing this and not me this year.
Sodium chloride. So we're talking about silver nitrate. That's AgNO3. And sodium chloride is NaCl.
So the silver nitrate is the same stuff that we saw making the Christmas tree just a few minutes ago.
You could write the equation like this, where the AQ, that stands for aqueous, dissolved in water. And the S, after the silver chloride, the AgCl, that's a solid. It's a precipitate. So here we're adding just normal NaCl to water. It's aqueous, it's dissolving.
So we're adding table
it's
salt.
Breaking apart into its ions. So we get Na plus and then Cl minus from the NaCl. They're aqueous.
So he's stirring up the salt water.
So we'll stir it up here a little bit. That'll speed up the dissolution. We also have AgNO3. We put water in there, we get Ag plus and NO3 minus. It dissociates or dissolves.
So he just made a solution of silver nitrate. And the reason why we want two solutions is to show that it's two liquids becoming a solid.
So now that we have these two aqueous solutions, the AgNO3 and then the NaCl, we'll mix them together. Remember, they're both aqueous, so they're split apart into their ions. When we do that, this is what happens.
It's also important that they're split up into their ions before so that they can regroup with each other in the solution.
Happens.
Okay, so he mixed them together, and notice it's forming this cloudy, murky,
AgNO3 and
milky
NaCl,
look.
they change places, a double displacement reaction, and we get AgCl, which is a solid. And that's a precipitate. It's going to fall over time to the bottom of the test tube or the beaker, and then what's left in solution will be those two ions, the sodium and nitrate ion.
So we call them spectator ions because they don't really do much. They're just there. They're not the ones participating. They're just like fans in a stadium. They're spectators. They're there, but they're not the ones impacting what's happening. So if you recall your solubility rules, silver mixed with any of the halogens, like chlorine, is going to be insoluble. That's why it's a solid. It sinks down to the bottom. Anything with an alkali metal like sodium or a nitrate, NO3, is going to be soluble, so it's just going to be an ion in solution.
So our chemical reaction took place there. And that chemical reaction would look like this. We have our AgNO3 and our NaCl both dissolved in water.
Okay, so we know they're dissolved in water because they say AQ.
React, and we get that AgCl plus NaNO3.
This is your precipitate.
The AgCl, the precipitate, silver chloride's at the bottom. It's a solid. If we poured the liquid off, let it dry out a little bit, that would look like this. So this is our solid AgCl, and in the liquid we poured off, that has the NaNO3. If we let that liquid that we poured off evaporate, that has the Na plus and NO3, that would eventually come back to be NaNO3, sodium nitrate crystals. This is Dr. B with the chemical equation for AgNO3 plus NaCl. Thanks.
Okay. All right, home stretch here. Okay, so that was two elements, two metals replacing each other to form two new compounds, one of which was a solid. So I'll let you think. What type of reaction has two metals switching places in order to form a solid precipitate of some sort? So think back on what we've learned over the past week. Okay, our last two videos are both about combustion. Okay, so this first one, she's sort of explaining what combustion is, just a quick refresh, since combustion was the first one we talked about. So let's take a look back and see what combustion is, what parts it has.
Hi, I'm Al, and I'm a science interpreter here at the Franklin Institute. And today, I want to talk to you about the chemical reaction combustion. Have you ever seen a campfire burn, or turned on a gas stove, or even seen a firework? If so, you've seen the chemical reaction combustion. A chemical reaction takes place when energy and matter combine. Combustion, the chemical reaction I'll be covering today, occurs when it gives an output of energy in the form of a fireball. Combustion is often referred to as burning. To create a combustion reaction, you need three main ingredients. The first ingredient you need is a fuel. That's like the wood in our campfire. The second ingredient you need is an oxygen source.
Recall that the fuel is usually a form of hydrocarbon. So it's got to have a lot of carbon in it.
We call this an oxidizer. Often it comes from the air around us. The last ingredient we need for combustion is a heat source. Again, for a campfire, you might use a match as a heat source to start that combustion reaction. When these three ingredients are combined, that's when you create combustion. So let's see some combustion in action. For today's reaction, I have these two iron spheres. One of them is covered with aluminum foil. The aluminum foil will be our fuel. Our second iron sphere.
So in this case, she does not have a hydrocarbon. She's using aluminum instead.
Has a layer of rust. The chemical name for rust is iron oxide. Iron and oxygen. That means that it can serve as our oxidizer. For our last ingredient, heat, we're actually going to use friction. You can experience friction if you take your hands and you rub them together. The energy you put into moving your hands is being lost as heat between your palms. But for this reaction, we're going to take that friction up a notch. These two spheres are very heavy. So when I slam them together, it creates enough friction heat to start our reaction. So let's take a look. for a spark of science. Now, please don't try these demonstrations at home, but if you like this sort of science, you can join us here at the Franklin Institute for live programming at the museum. Thanks for watching.
All right, so now that we've had a refresher of combustion reactions, let's finish this off with burning alcohols. Okay, so this one actually gets a little fun. So what this guy is doing is he has 3 different alcohols, methanol, ethanol, and isopropyl alcohol, which is rubbing alcohol. And he has soaked some sponges in them, and he's going to burn the sponges. Okay, now I want you to watch what happens to the flames, particularly the color of the flames. So he's going to come and explain it.
I'd like to demonstrate for you the effect of increasing numbers of carbon on the combustion of alcohols. So I have 3 alcohols here with increasing number of carbons. I have methanol, a 1-carbon alcohol, ethanol, a 2-carbon alcohol, and isopropanol, a 3-carbon alcohol. We're going to combust all 3 of these and observe the similarities and differences upon their combustion. In each container, I've placed a cut piece of a Mr. Clean Magic Eraser. And that's going to soak up the alcohol, and then we'll be able to burn them more easily. So first I'm going to test methanol, the 1-carbon alcohol. I'm going to go ahead and remove the piece of sponge, recap the lid, and I'm going to remove the alcohols from the burning area. We'll light this on fire. And what you note is primarily a blue flame. Now, blue flame is indicative of complete combustion. That means that the ethanol is being completely converted chemically into carbon dioxide and water. You might notice a few flecks of orange and yellow. Those are regions of the flame where the methanol is being incompletely combusted. And in that case, there's some soot formation. And when soot gets hot, it incandesces or glows an orange-yellow color. But mostly, what we see here is a blue flame indicative of complete combustion of the methanol. Now, to sort of show that no soot's being formed, I can take a clean test tube and place it in the flame. I'll run that back and forth. I can actually see some condensation of product water on the test tube originally. Now it's sort of burnt off.
So he's trying to see if any black residue is left
in the
behind.
film. Well, sometimes I can blow that out, but oftentimes we have to just stick it in a beaker of water. But if you look at the test tube, you will not see any soot.
It's clean.
That's evidence of complete combustion.
No waste.
Now we're going to test our second alcohol, ethanol. So we'll get this out, and we'll burn the ethanol. And in this case, we notice quite a bit more yellow-orange color. So we see that the ethanol is undergoing some incomplete combustion. But if you look down near the bottom of the flame, right around the sponge, you'll notice that the flame is blue. So at the bottom, originally, when the fuel is first burning, it's burning completely. But as the flame rises, it actually gets a little oxygen deficient, and it's a little more difficult for the fuel to combust completely. Once again, we can do the test tube test to look for the formation of soot. And what we recognize is that even though the flame was quite yellow, there's not much evidence of soot formation. So even though we saw evidence of soot formation in the burning of the ethanol, there's not enough soot being produced to form a lot of residue on this test tube that was placed in the flame.
So in other words, it's not as
Now
effective as the methanol, but it's still okay.
Isopropanol. And one might hypothesized that because the methanol, a one-carbon alcohol, completely combusted, the two-carbon alcohol, ethanol, showed some signs of both complete combustion and incomplete combustion. One might surmise that the isopropanol, which is 3 carbons long, will follow this trend, and we should see a lot more incomplete combustion rather than complete combustion with the isopropanol. Let's run the combustion reaction and find out.
So this is rubbing alcohol. There's a lot of yellow in
What you
there.
notice with the isopropanol is a very bright orange-yellow flame. That is indicative of incomplete combustion. Very little blue in the flame. So there's not much complete combustion going on. I'm going to take this test tube here and run it through the flame.
Notice what
And
you see on
almost
the test tube.
immediately, you can see the formation of some sooty residue on the test tube.
So that
So in
means there was
summary,
so that means there was some waste in there.
what you basically see as you go from a 1 to 2 to a 3 carbon alcohol is that the lower the number of carbons in the alcohol, the more completely it combusts, and the greater the number of carbons in the alcohol, the more incompletely it tends to combust. The 2 carbon alcohol ethanol showed signs of both complete and incomplete combustion.
All right, so that's it for our lab today. Be sure to note down any observations that you made for each section of the lab. I'm going to post this video on the Google Classroom page separate from the Edpuzzle so that you can rewatch it if you want to. You probably will want to while you're writing your lab report. Okay, so that's it. Hope this was helpful and better than just watching individual clips with no narration.